All right, so in this video I want to talk about linear transformations. Probably should have sipped that coffee before hitting record, but whatever. So linear transformations, um, let's define it. So let u and v be vectors in Rn. And then we can say then t from Rn to Rm is a linear transformation if, and then there are two properties, they both have to be met. So one, t of u plus v equals t of u plus t of v, and two, t of c times u, where c is a scalar, let's say, and c is a scalar, so we've got all our bases covered, equals c times t of u. Now, if you could actually think of functions in R2 that look like this, they'd all be lines right through the origin. Not that you really need to think of it that way, but I'm wondering if that's where the phrase linear transformation comes from. So anyway, this right here, we say that this means that the transformation preserves addition. Remember well, actually, I don't know which order you're watching these videos in, but in orthogonal transformations, we actually showed that it preserves the dot product, preserves norm, preserves angle, all that kind of stuff. This one preserves scalar multiplication. So let's talk about, so this is the definition, right? Definition here. So then we've got some properties. Actually, you know what? Let me put some lines on here. I can't do this without lines easily. Okay. So let's look at some properties of linear transformations. Sorry, just abbreviating a ton here. Okay. So these are the ones besides the definition. The definition is the main thing here. So one thing is in matrix form, not yet. Sorry, in matrix form, we can write T of U is the same thing as A times U, where A is some matrix. And then here, note, it turns out that every single matrix transformation is a linear one. And this actually isn't too hard to prove. In order for us to prove it, we need these two properties right here. We need this and we need that. So, well, let's look at it, right? If I take A times U plus V, well, we learned before that that's the same thing as just AU plus AV. So property number one is met. And then property number two says, if I have A times C times U, where C is a constant, we're allowed to just pull that out. So it becomes this instead. And we learned that a while back too. So that's met. So we've got property one and property two. So every matrix actually defines a linear transformation. Any matrix you want. You just need the right size vectors to go with it. So this is one property. Here's another property. Turns out that you always map. So any linear transformation will map the origin back to the origin. Right? So that means T of the zero vector Well, that's since it can always be represented as a matrix transformation, it's A times the zero vector, and any matrix times the zero vector is the zero vector. So if I start with the zero vector in Rn, then I get the zero vector in Rm, and that's the same thing as saying the origin in one space maps to the origin in another space. Some other stuff, we're not going to prove them all, but if I have a straight line in one space, straight. So straight lines in one space are mapped to other straight lines. And then, let's see, what else? Oh, also, parallel lines are mapped to parallel lines. And length ratios are preserved. Okay. One more definition here. So this is no longer properties here, but so this is a new definition. A linear transformation T from Rn to Rm is 1-to-1 if it maps distinct points, or depending on how you want to consider your inputs, you could call these vectors instead, in Rn into distinct points or vectors in Rn. Now that's really the same one-to-one definition that we've studied like 2 or 3 other times this year. So that's not really anything new here. And then there are a few conclusions you can draw from this. So let's see here. If A is an n by n matrix, and the transformation we're looking at, Rn to Rm, can be represented by T of u equals AU, then these 3 statements are equivalent. So the first one, now they don't mean you need all 3 statements to prove something. It means if you know one statement, you know all 3. So the first one is A inverse exists. So if you have an invertible matrix, that means I could use A to map a bunch of points into some other points, and then I could use A inverse to map those new points back into the original points. And since I can really take a matrix and multiply by any vector I want, as long as it's the right size, and if I'm supposed to get reversible processes, that means that I should be able to map anything I want in the first world into anything I want in the second world. And oops, sorry, this has to be the same size, n, because A inverse has to be n by n. So this here, the range of T equals Rn. And then the third thing is T is 1-to-1. So if you know any one of these 3 things, you know the other 2 as well. Let's see, how long is this video getting? Okay, so I'm going to stop here in this video, and then there's one more video where I'll do a couple of examples using linear transformations so that you can see how they work, how to prove something's a linear transformation, because it doesn't always make sense right off the bat, but after you do an example or 2, it's not that bad. Okay, I'll see you guys soon.